If you look at this picture which I drew in the last lecture, based on our concept of static stability, we said that all points on this side of the drag curve are unstable equilibrium states. If we just go by balancing thrust equal to drag and not really caring about the other degrees of freedom in this motion, and on the other side what we found was that all the equilibrium states are stable, right, and this we can obtain, all the states we can obtain by changing the thrust available. Now, in reality, it is not true that all the states are unstable on this side of the curve. The reason is that when we are talking about static stability, we are actually talking about only the system's tendency to come back to its equilibrium state, and not really seeing if it has really come back to its equilibrium state or not. So, there is another notion of stability which is related to, which is dynamic stability, is related to the actual time history of systems state, right. So, what we do in this case, we look at the response, and we look at the response at time t going to infinity, and see if the system has really come back to its original equilibrium state or not. So, here x equal to 0 is the equilibrium state, and because of the external disturbances or perturbation, this is the response in x from this equilibrium condition, and we look at the time history. So, if the transients have died down and the system has achieved this state again x equal to 0, then we say that the system is, or our airplane is dynamically stable at an equilibrium state when it eventually So, clearly it looks like that this system for which I have written this state x and plotted it against time. So, it clearly looks like the system is having a tendency to go back to its equilibrium condition. So, what it is telling me is that system is statically stable at this equilibrium condition, and since the transients have also died out in time, and system is able to come back to this 0 equilibrium state, it is also dynamically stable, right, from this definition. So, here statically stable does mean dynamically stable equilibrium condition. What actually you need to do when you want to look at the dynamic stability, you need to find the solutions of system's equations of motion when it is disturbed from the equilibrium condition. So, let us look at a simple example, again the example of this pendulum. So, we already wrote equation of motion for this pendulum. So, we have, so physically we already see that the system is statically stable at this equilibrium position, and we want to see that mathematically also if it is, so static, this position is statically stable, that is what we said. Now, we want to do the same analysis through this equation of motion. Now, clearly we are talking about the stability, we are talking about small motion around this equilibrium states. So, we are actually talking about theta, which is small. Remember, theta is a change in state, small change in state of the pendulum because of a small disturbance. So, this when we try to associate this with stability. So, theta is small, sin theta, there is a nonlinear equation of motion which is not really easy to solve. So, we want to look at simpler ways of looking at stability without looking at the actual time response for this equation. So, sin theta is theta, and when theta is small we can make this approximation. And the equation simplifies to this linear equation, and this simplification has been done around theta equal to 0 equilibrium state. Now, solution for this we know, we can write the solution for this equation in terms of the parameters. Omega is the natural frequency, and A and B depend upon the initial conditions. Okay. So, if we have an initial condition which looks like theta at time t equal to 0 is 0 and okay, the velocity is non-zero, then you can also write this theta t as, or let us do one more step. So, when theta is 0, theta at time t equal to 0 is 0, what we get from here, from this solution, is a into 0 plus b into 1, and that gives us b equal to 0. So, we have solution for this initial condition as theta of t is equal to a sin omega t, where a is given by this initial condition, and what we get is so clearly depending upon the impulse that you will give to this mass to make it move away from this equilibrium condition, will result in the amplitude of the motion. So, if I want to plot this response, it is going to look like this. Now, the question is, how do we infer about the stability from here? Clearly, the system is this mass m is statically stable about this equilibrium position, which is theta equal to 0, right. Statically stable because it's coming it has a tendency to come back to this equilibrium state. So, it's statically stable. Is it dynamically stable, this equilibrium condition? No. Okay. So, this equilibrium condition for this pendulum is theta equal to 0 equilibrium condition for this pendulum is not dynamically stable, because a dynamically stable response will look something like this. The transients decaying in time, so that system has finally reached this position of equilibrium in time when t goes to infinity mathematically. So, it is not dynamically stable, but statically stable. So, what you get from and stability actually have to be with respect to the dynamics. So, what you can infer from here is statically stable does not always imply statically stable does not always imply that the system is also dynamically stable. So, this is clear from this exercise, while the other way around it is true. When a system is dynamically stable, it is also statically stable. But this is also useful, because the problem is when you want to look at the dynamically stable or dynamic stability of an equilibrium state of the system or the airplane, what you need to do is we need to incorporate all the parameters, use all the equations and solve all the equations together to find the solutions with respect to time, and then look at the time history and see if the tangents are decaying in time or not. So, clearly clearly there is an advantage of using static stability criteria. There we just have to look at how the restoring forces are behaving with respect to the change in state of the system, and we can from there infer about we can get some information about the stability of the system. But in this case we have to look at the equations of motion, which is more difficult. And if you want to talk about aircraft, an aircraft designer will usually will have a lot of difficulty generating all the data possible at the preliminary design itself, stage itself, so that he can carry out the dynamic stability analysis. So, what he would rather prefer is to look at to start with, once he has come down to some design meeting the mission requirements or the performance requirements, then what he would be interested in knowing about stability is some information. It is not the complete information, because it may not be possible to do that, because aircraft is having 6 degrees of freedom, 3 in translation and 3 in rotation, and it has lot many parameters, which is not difficult to generate at that preliminary stage. So, there are established criteria to be followed by aircraft designers. So, what they would start with is looking at static stability first. They would want to get first hand information about if the aircraft really has the tendency to restore itself to the equilibrium state or not, and then based on that he can go on building the aircraft. He can include many more design parameters in the aircraft model, and finally come to a stage where the aircraft model or the mathematical model, the ordinary differential equations, is complete, and then he can go on doing the dynamic stability analysis. So, and dynamic stability is also related to static stability. No, is only in some cases which are critical cases. Otherwise, it's possible to infer something about dynamic stability by looking at static stability. So, there are different stability criteria that an aircraft designer would start with, and they are related to different flight conditions. So, there is one, so this is basically the stability criteria, static stability criteria, which are basically guidelines for aircraft designers, are based on is actually rotational motion about the CG in different planes. So, first of that is longitudinal static stability, and this is related to this derivative. So, so m here is the pitching moment. So, what this means is, whenever there is a change in angle of attack because of gust can change the angle of attack, and there is a change in angle of attack in the positive direction, what is happening to this pitching moment to ensure static stability. So, it is not difficult to see that whenever there is a positive change in angle of attack, which is also associated with the pitching up motion of the aircraft, if this pitching moment should be automatically generated, not that we are looking at the control side, we are not looking at controls. Stability is the inherent property of the aircraft. So, as soon as there is a disturbance, and that disturbance is creating a pitching up motion of the aircraft. So, delta alpha is changing in the positive direction. Now, if whether the aircraft is able to, so aircraft is pitching up when there is a positive change in angle of attack. So, aircraft is pitching up, whether the aircraft will naturally try to generate a pitching moment in the direction to decrease the delta alpha or not, that is related to the static stability of the aircraft, in this case longitudinal static stability. So, for longitudinal static stability or the pitch stability, and this is control fixed. So, control stick is fixed in this case. So, we will later on look at what happens when the pilot leaves the stick free at the trim point, but here let us first begin with looking at the control fixed or stick fixed condition at the trim point. So, this delta alpha that is due to external disturbances causing a pitching up motion will have to be counteracted by the aircraft. So, aircraft has to kill this change in positive delta alpha because of the which is coming because of the external disturbances. So, it has to automatically generate a pitching moment in the other direction, so that this delta alpha is killed. So, what you see here for this will be a statically stable condition. So, aircraft will have automatic tendency, natural tendency to generate a restoring moment which will try to kill this delta alpha, and that is when we will say that aircraft is having static stability properties. So, this writing it in mathematical terms, this derivative must be less than 0 for static stability and pitch. M is the pitching moment. So, M is Q into S into C bar into Cm. Cm is the pitching moment coefficient. Now, these three quantities remaining constant, you can also write this derivative as dCm over d alpha, and sometimes it is also written as Cm alpha should be less than 0 for pitch stability. Many times you will also see Cm alpha as dCm over d alpha, or the stability criteria also written in terms of dCm over dCl. And this clearly comes from here. So, you can write dCm over d alpha as this is positive. So, dCm over d alpha less than 0 automatically also implies okay. So, let us look at this graphically. Okay, let us plot Cm versus Cl. So, remember all the moments are about the center of gravity of the airplane. So, clearly if we want our aircraft or airplane to possess stability in pitch, we should have a Cm versus alpha curve which looks like this. So, this is a stable case. So, an aircraft having Cm alpha curve which is having a negative slope is possessing stability, static stability in pitch. The aircraft having dCm over d alpha equal to 0 is a neutrally stable aircraft, and this aircraft 3 is having a positive Cm alpha slope, and therefore, we say that is statically unstable airplane. The other thing that also the aircraft designer has to keep in mind is not only about satisfying this just this criteria. You can satisfy this criteria even when you have this Cm versus alpha profile like this. So, here clearly you have Cm alpha less than 0, but what is happening in this case is this curve is cutting the alpha axis at negative angle of attack, right. So, this if the aircraft is possessing stability, but is having a slope like this, what is resulting in is the Cm naught, which is the Cm at alpha equal to 0, which is negative. Cm naught negative automatically means Cm naught negative and Cm alpha less than 0. So, both of them negative means that the aircraft is statically stable in pitch, but it can trim only at negative angle of attack. Okay. So, Cm less than 0 and Cm alpha less than 0 is telling me that the aircraft possessing these two characteristics, craft is statically stable in pitch, but can trim. Now, trim condition is defined by this equation. If we are looking at the moment equation, then we have to satisfy Cm equal to 0, Cm Cg equal to 0 for the trim condition. So, here is where the Cm becomes 0, and that is giving me alpha which is negative. Right. So, the aircraft is possessing these two characteristics, is statically stable in pitch, but can trim only at negative Now, clearly we do not want to trim our aircraft at negative angle of attack, because that is very unrealistic, because if you look at the lift versus angle of attack curve, with angle of attack lift increases, and that is what we want to maximize. So, we would never want to actually fly negative angles of attack. Okay. So, two things that an aircraft designer will keep in mind as far as this pitch this Cm alpha curve is concerned. One thing is the aircraft must have Cm naught which is positive and Cm alpha which is negative. So, this is to trim at positive angles of attack and Cm alpha less than 0 to have static stability and pitch. Okay. So, we in the coming lectures what we will see is how different components of aircraft are contributing to Cm naught and to Cm alpha. This is what we will look at in the next few lectures, but before that let me just complete this. So, this is the criteria in for stability in pitch. There are criteria for stability in roll. And that criteria is this. So, change in rolling moment coefficient with respect to change in side slip angle must be negative. This is also known as we are going to see this again. So, this CL is coming from the rolling moment. So, this is another static stability criteria that the aircraft designer will have in mind. And the third one is, so you can see that clearly we are talking about the stability with respect to the angles alpha and beta, and that those are the angles which are defining the orientation of the wind with respect to the aircraft. So, we are looking at disturbances in alpha and beta, how they are going to change the moment characteristics. The third one is the stability of motion in yaw. And the criteria for this is del Cn over del beta should have a positive sign. So, this derivative is also written as CL beta. So, Cn here is the yawing moment So, as far as the static stability part is concerned, we are going to look at these three derivatives and what are the contribution of each of the aircraft components, components mounted on aircraft, either mounted on aircraft or constituting the aircraft, how they are contributing to each of these terms Cm alpha, Cl beta and Cn beta, right. This is what we are going to see in the following classes.